Well, hello there. This is the first lesson of many on trigonometry in this course, the first lesson from the second unit of the course. Now, trigonometry in this course covers 3 chapters, 4, 5, and 6 in the textbook, each focusing on something different. The main difference about trigonometry in this course compared to what you've done before is very, very little of it has anything to do with triangles. You can kind of imagine it as you've covered all the basics of, right angle and non-right angle trigonometry. Now we want to start seeing how we can start to apply these things to rotations, which is much more involved, and it'll feel quite different, although, as I always say, everything is all connected. Each of the 3 chapters focuses on a different aspect of this sort of type trigonometry. Chapter 4 that we're starting here is more focused on understanding how to think of trigonometric ratios in terms of rotations and understanding radians. Chapter 5 is more understanding especially sine and cosine as functions that have inputs and outputs and can be graphed and transformed and be used to model scenarios. And Chapter 6 is looking at how all trigonometric functions are actually interrelated to one another. And there's all these connections, algebraic connections between them all. And that's the most algebraic of the 3 chapters. So with that said, let's get straight here. A radian is actually a unit of measurement for angles that we're going to use almost exclusively in this course and any calculus course. Essentially, degrees, which you're used to thinking about, are fine and all, but they're not very useful for calculus. They're quite unpleasant, actually, for dealing with calculus, whereas radians are quite pleasant for calculus. And so first, what's a radian? Well, a radian is much different than a degree in terms of size. This, what I'm kind of coloring in yellow, is 1 radian. Whereas 1 degree is, if I was to estimate 1 degree visually, 1 degree would probably look something like, it would be so hard to draw because it's so small. 360 of them fit in 1 rotation. So let me get rid of that. So what defines a radian? For example, a degree is defined by its 1/60th of a rotation around a circle. What's a radian? A radian is determined. It's determined by the angle when the arc length, which is this part here, is the same as the radius. So notice when I'm drawing in red, all these 3 of these lines are actually the same length. So the 2 here, those are clearly the radius. Each is a radius of the circle. But if you imagine this slice getting large enough so the 2 radii are the same length as this arc length out here, if you imagine a slice where all 3 of those lines are the same length, then that's what 1 radian is. So keep in mind, if I drew a slice like this, clearly this chunk, this arc we call it on the outside, is far shorter than these. So that's less than a radian. And if I draw an arc that's like this, I hope it's pretty clear that this arc length I'm drawing on the outside of the circle is definitely longer than the radius of this circle. So that's more than a radian. A radian is when the arc length on the outside is exactly the same as the radius. And that's what you see here. All right. Now, let's compare radians to degrees. You've been dealing with degrees for years. You may have never dealt with a radian before. We need to start thinking about radians more and more. But first, 360 degrees, which is 1 full rotation, is equivalent to 2 pi radians. 2 times pi, so about 6.28 radians. But instead of saying about 6.28 radians make a full rotation, let's say 2 pi does. And so knowing that, all the rest we can kind of figure out by what we call proportional reasoning. For example, 180 degrees is half of 360, so in radians it must be half of 2 pi, so 1 pi. 90 degrees is half of 180, and so half of pi must be the equivalent in radians. 60 degrees is 1/3 of 180. So in radians, it must be pi over 3. 45 degrees is 1/2 of 90. So radians must be half of pi over 2, which is pi over 4. And 30 degrees is half of 60, for example. So in radians, 30 degrees must be half of 1/3, which is 1/6. So first what I have here, and I'll erase these little arrows, this needs to be memorized as soon as possible, all of these. I cannot stress the importance of memorizing these as soon as possible. Honestly, what is there? 6. Memorize them. I mean, it really shouldn't take you long at all to memorize. You just have to make a point. You will not be allowed a calculator for assessments in this first chapter and the mini test. So if you think a calculator can keep you from memorizing these things, please don't rely on that. Just memorize them. It's not much at all. That said, what is 1 radian in degrees? Not 1 pi, 1 whole radian. Well, that's what I've drawn right here. What you see in yellow right here is 1 radian. What's that in degrees? Well, I can still use proportional reasoning here. For example, to go from here to here, to go from 2 pi down to 1, I have to divide by 2 pi. That's the messiest writing I've ever done. Let's try that again. To go from 2 pi down to 1, I want to divide by 2 pi. So if I can do the same thing here, or even, yeah, let me actually make this a bit nicer. That's not wrong what I said. But I'm going to go from 180 degrees. To go from 180 down to pi, I want to divide by, oh, I keep speaking incorrectly. Shocking, I know. To go from pi down to 1, I have to divide by pi. So do the same thing here. Divide by pi. And so therefore, 1 radian must be the same as 180 degrees divided by pi. Which, if you approximate it, if you decimalize this, you get approximately 57 degrees. Let's see if I can make that a bit neater. Okay, so 1 radian is about 57 degrees, and that's what you see, that slice there. You know, it's just shy of 60 degrees. In general, though, what about just pi radians? Just any number of radians. Well, that's going to be the same as 180 degrees divided by pi. So, and take all that and times by the number of radians you have. So if you know your angle in radians, multiply that angle by pi over, sorry, about 180 over pi, and you have the answer in degrees. And if you want to go the other way around, if you have an angle in degrees, you want to take that angle and multiply by pi over 180. And these are ideas we explore in some of the group problems. That's it. Of all of these, the most important ones are those ones I've highlighted at the top. Those are knowing those quickly, knowing that half a rotation is pi radians is far more important than knowing how to convert like this. We're not actually going to use these conversions very much, or what I kind of formalized down here. We are going to use these all the time. All right, so that's it to formalize basically these last 2 parts of the table. To convert radians into degrees, you multiply by 180 and divide by pi. And if you want to convert degrees into radians, it's the other way around. You multiply by pi and divide by 180 degrees. And everything you see right here is equivalent to what I showed right here. And this can all be figured out by that same sort of proportional reasoning. Again, by looking at something we know from up here, figuring out the proportion about how we go from one number to another, that's how we can figure out all of these. But again, the ones at the top, where I said memorize, are by far the most important. So please, memorize them. All right, next, hopefully review of what angles and standard position are. It's a standard way, conventional way of showing a rotation on a coordinate plane. And so first what I have here in gray is the xy coordinate plane. This is the x-axis, this is the y-axis. And so this is the origin, 0, 0. These red and blue arms we show here, these are visualizing a rotation. And the one in red is the initial arm. And that's by convention, we always imagine, if we show an angle in standard position, we imagine a rotation starting right where I have this red arm. We call that the initial arm. The one in blue is where the rotation has ended. We call that the terminal arm, terminal meaning end. So, if we think of this as a rotation, you may very well imagine this rotation looking like this. And that rotation we call theta, or any other variable, but theta is the most common variable to give to a rotation. That said, if all we know is where rotations begins and ends, how do we know it didn't go backwards? And honestly, we don't. If all you know where a rotation begins and ends, you don't know how it got there. Or how do you know it didn't go backwards a whole bunch of times before stopping here? And like I said, we don't. And so I'll keep this first example, which I think is kind of the simplest to visualize. But like I keep saying, if you know where a rotation began and where it ends, don't assume you know exactly how it got there. Some other things that hopefully sound familiar. This angle formed between the terminal arm and the x-axis is called the reference angle. And usually I'll just use the symbol theta with a little r. And it's always between 0 and 90. It's always an acute angle, and it's formed between the x-axis and the terminal arm. What else do I have here? Let me just kind of visualize roughly what theta is here. So this angle of theta is definitely more than 90 degrees. A good estimate would be about 135 degrees. And I went with 135 because I'm estimating this reference angle to be 45 degrees. Because it sure looks like it's roughly halfway between the x and the y axes in that quadrant. And so if that's 45, this angle I've shown in blue must be 180 minus 45, which is 135 degrees. Now that's in degrees. In radians, that would be 3 pi over 4. And how do I know that? I have a few options, but let me tell you what I think is by far the best option of quickly converting 135 degrees and thinking about it in radians. If I go back up here, one thing I do not recommend doing is using either of these to think about what 135 degrees is. What I would do instead is realize that 135 degrees is the same as 45 times 3. And I can visualize that right here by, that's 45 degrees, that's 45 degrees, that's 45 degrees. So visualizing these things. And so once I realize that 135 degrees is the same as 45 times 3, well then 45 degrees, I already mentioned right here, is pi over 4. So 135 degrees must be the same as pi over 4 times 3, which is 3 pi over 4. So always coming back to these angles that I've asked us to memorize and using them to proportionally reason what angles in other quadrants would be, as long as they're multiples of these, can be pretty fast. If you always go back to one of these formulas to convert, it's pretty slow. All right, with that said, the last thing I want to comment on here is that if an angle is a positive number, like I've shown here, it's going the direction you see, which is counterclockwise. So if theta is a positive number, then the rotation is counterclockwise. And that's what I've shown with that arrow. And so hopefully, again, you knew this already, or it sounds familiar. If an angle is negative, if an angle is less than 0, then it's going the other direction, which is clockwise. So of all of this, the only part that's new to this course is the radians part. All the other terminology here I'm hoping sounds familiar, and I've kind of refreshed your memory of it. That's it. The term coterminal. All that means are coterminal angles, or angles in standard position that end up in the same place. So for example, in the example I have above, I said theta was 135 degrees, or 3 pi over 4. So some coterminal angles would be, visually, let me look here first, I'll make a bit of a mess of this and then erase it. Another coterminal angle would be an angle that goes backwards like this. That angle I just showed in red is coterminal to 135 degrees. How could I figure that out? Well, one way is to realize that from here to here is negative pi radians, or negative 180 degrees. And then this little chunk right here is an extra 45 degrees backwards, so another 45 degrees, or minus pi over 4. So altogether, that would be negative 5 pi over 4 radians, or negative, what would that be? Negative 225 degrees in degrees. Okay, that's one way of visualizing it. Or, what's probably easier, there's nothing wrong with that, is to realize once I know that this angle in blue is 135 degrees, if I just take that from there and go backwards one full rotation, that must be the same number. And so if I go 135 degrees minus 360, that will lead me to that same number of negative 225. Or if I go 3 pi over 4 and minus a full rotation, 2 pi, that will, once I combine like terms, lead me to that same minus 5 pi over 4. And so that idea of just subtracting or adding a full rotation to any other angle, you know the angle must end up in the same spot. So that's probably the fastest way to determine if something is coterminal. Just take whatever angle you have and either add or subtract a full rotation. So again, for our notes, first I'll start in degrees. So again, if we're dealing with 135 degrees, let me write that down. So I mentioned already, if I subtract 360 degrees, I know that angle must end up in the same spot, which I already said is negative 225 degrees. If I add 360, I know that angle must end up in the same spot, which would be 495. And I know I can just keep doing this on in either direction. And so I know there must be an infinite number of coterminal angles that all end up in the same spot. An infinite number of angles that all have a terminal arm in the exact same spot. So I can actually generalize this list that goes on forever. I can generalize the list by picking one angle. I'll pick the smallest positive number and say, if I want to generalize all of them, actually I'll say it in general first. In general, what's going to be coterminal? Well, 135 degrees plus any multiple of 360. And one way of showing that is to say n times 360 degrees. But then I need to specify that n can be any whole number or any negative number. If n is negative 3, that's the same as subtracting 360 3 times. But how do I specify that n has to be a whole number or a negative number? That means n has to be an integer. So I say where n belongs not to the real numbers, but to the integers. And the textbook uses a capital I to represent integers. A more typical way actually is using a capital Z, but the textbook uses an I, so I'll do that. And so this statement here summarizes all the angles coterminal to 135 degrees in degrees. So what would be the same thing in radians? Well, let me start with 3 pi over 4 radians. Okay, same angle. Oh, it is really raining outside. Oh, it's like the end of the world out there. Okay, hopefully the world doesn't end when I'm making a math video. Anyways, so here the exact same idea is I can first add or subtract a full rotation, which in radians is 2 pi. And 3 pi over 4 plus 2 pi is actually pretty pleasant to do once we find a common denominator. And so instead of adding 2 pi, really what I'm doing is adding, it's more convenient to add 8 pi over 4. Can you hear that rain? It's crazy. Anyways, I really just found a common denominator of 4. And so 2 pi over 1, same as 8 pi over 4. And now, once I think about 8 pi over 4, 3 pi over 4 plus 8 pi over 4 is 11 pi over 4. And I could go on and on and on. Same thing for subtracting. If I want to subtract 2 pi, it's probably actually more convenient for me to subtract 8 pi over 4. Again, all I did was found a common denominator. And 3 take away 8 is negative 5, so negative 5 pi over 4. And on and on and on. Okay, and so I could keep doing that, but my list will never end. So let me generalize this. So in general, all my angles coterminal to 3 pi over 4, I can say is just pick one. I'll pick 3 pi over 4 plus any multiple of not 360 degrees, any multiple of 2 pi, where again, n can't be any real number, it can be any integer. Keep in mind, if n is negative 5, and I replace that n with negative 5, that means I'm subtracting 2 pi 5 times, right? Adding a negative, same as subtracting. And so if I let n be any integer, this takes into account options when I subtract as well. And remember, we will deal, especially as the unit goes on, more almost exclusively with radians. And if you take calculus, you will deal essentially exclusively with radians. Degrees are not very pleasant for what you want to do in calculus. All right, so generalizing coterminal angles, which again, coterminal angle just means an angle that ends up in the same spot. Lastly, final problem. So I have a point that is the intersection between the terminal arm of an angle of 11 pi over 6 radians in standard position and the unit circle. The unit circle is a circle with radius 1, and that's what's shown. So first of all, that sentence I read has a lot of terminology, and it's quite to the point, but if I didn't actually have to give this visual, I'm sure the visual helped, but let's notice what we have in the visual. So point P is just, it says the intersection. So that's that point right there. It's the intersection. It's where two things cross. Between an angle of 11 pi over 6, between the terminal arm, I should say, of an angle of 11 pi over 6. And so 11 pi over 6 is this angle from here to here. I know it's going that way because it's a positive angle. I know it's not going backwards because otherwise it would be negative. So that there is 11 pi over 6 radians. I'll put theta. and it's where it crosses the unit circle. The unit circle, which is actually the title, I believe, of the next lesson, is, like it says, a circle with a radius 1. And so if I look at this circle here, it's centered on the origin, and you can see all the coordinates on the circle are all either 1 or -1. So I can see it has a radius of 1. So our task is to find the coordinates of P. This point right here. What are the coordinates of this point? X comma y is what? That's what we're trying to figure out. So eventually our goal would be to be able to visualize this diagram without actually being given the diagram, just from what's described. Because from what's described, we know there's a circle with radius 1. We know there's an angle of 11 pi over 6, which we can start to visualize. And we know that the point is where that terminal arm crosses the unit circle. That's it. How can we figure this out? Right now, it's not a bad idea to change this into degrees. And 11 pi over 6 is pretty easy to change into degrees if I just think about what pi over 6 is. So note, pi over 6 radians is the same as 30 degrees. That's from what we saw at the very beginning of the lesson. So therefore, 11 pi over 6 must be the same as 11 times 30, which is 330 degrees. So that angle I showed you in radians is the same as 330 degrees. And since you're probably much more familiar with degrees, it's not a bad idea at all to change it to 330 degrees right now. Just don't always do that as the course goes on. Which means, if I look at this triangle here, if that angle in red is 330, this little angle in here must be 30 degrees, which is what we call the reference angle. Right? It's the angle formed. My God, the rain. It's crazy. I'm going to get flooded here. I'm talking over rain. The 30 degrees is that reference angle right there. Okay, how does that have help? Because I can now imagine there being a right triangle if I draw a vertical line straight from this mystery point up to the x-axis. And as well, since I said this is the unit circle, I know the distance from here to here must be the same as the radius, because I literally have highlighted the radius, and that must be 1. And I've now drawn aspects of a triangle that I'm hoping looks familiar, because this triangle I've kind of drawn is what we call one of the special triangles, which was part of pre-calculus 11, and quite often it's introduced in grade 10. So there's a few types of special triangles we need to memorize in an earlier course, and one of them, the 30, 60, 90 triangle, looks like this. There's a 30-degree angle here. Make this a little bit neater. So from memory, if we have a right triangle with a 30-degree angle and a 60-degree angle, we know one way of memorizing it is the hypotenuse is 2, the shortest side is 1, or more importantly, the shortest side is half the length of the hypotenuse, and the side in between is root 3. Okay, so that's what we call it's one of our special triangles. That you're expected to memorize in pre-calculus 11. We call this a 30, 60, 90 triangle. But who cares what it's called? And so how is that of use to me? Because if I look at my diagram right here, if I want to find the coordinates, I really need to find the length of this line right here. I'll call that x. I need to find the height of this line right here, which I'll call y. If I can find those distances of that triangle, I have found my coordinates, essentially, with just one difference. And so if I look at this triangle here, I know the hypotenuse is 1. I know one of the angles is 30. So let's find x first. I can find x because from 30 degrees, I know the hypotenuse. I'm trying to find the adjacent side. Adjacent and hypotenuse is cosine. And so I can use cosine to find x. So I'll start by saying over here to find x, I'll say the cosine of that 30-degree reference angle. And I'll stick with degrees for a moment because it's not wrong and it's more familiar. Cosine, again, is adjacent over hypotenuse. In this case, it's x over 1. Well, dividing by 1 is kind of silly. So I have the cosine of 30 equals x. So how do I figure out x? Well, I could use a calculator, although not in a test in this unit, in this part of the unit. If you were to use a calculator, you'd use the inverse of cos. And eventually essentially what you're doing is you're using the inverse of cos of both sides to cancel that out, but we don't want to do that because we're not using a calculator. Cosine of 30 degrees equals x. What am I talking about? I don't use the inverse of cos. Oh, I'm far too lazy to re-record this entire video because of these mistakes. Anyways, I'm going to blame the rain. It's the rain outside that's distracting me. I always blame the rain. And so the cosine of 30 degrees, I can just find, still using a calculator if I was allowed to, or by looking at my special triangle right here, I know the cosine of 30 must be adjacent over hypotenuse. And so in this case, it's root 3 over 2. And so that is not only my x, that is going to be the x coordinate of my point right here. And same idea for finding y. If I want to find y right here, from 30 degrees, y is opposite to the angle. And again, 1 is the hypotenuse. Opposite and hypotenuse is sine. So if I use the sine of 30, I can find that y distance. I'll try not to screw up this time. That's it. We all make mistakes. So the sine of 30 is going to be y over that 1, or just the sine of 30 equals y. And looking at my special triangle, from 30 degrees, sine is opposite over hypotenuse. And so from 30 degrees, sine is 1/2. And so lastly, I found the distances of this triangle, but don't forget I want coordinates. So if I look at my coordinates right here, my x coordinate is going to be exactly root 3 over 2. My y coordinate is in the 4th quadrant. It must be negative, so it's not 1/2, it's negative 1/2. And that's the coordinates of P. So aside from my few little errors, misspeaking a bit, while there was a lot of things for me to explain here, there wasn't a lot of work. I mean, algebraically, I converted into degrees, but that was quick. And I did some simple right angle trigonometry. Ideally, though, again, I would highly recommend anytime you have an angle that's any multiple of 30, 45, or 60, you don't need a calculator, and you will not be allowed a calculator on the first part of this unit. So really avoid using a calculator unless I'm explicitly telling you to. So again, in this case, we have to just remember this. And eventually, we'll want to just memorize some key aspects of sine and cosine and tangent. But right now, you want to just refer back to those special triangles. So the first of a lot of parts on trigonometry. And while I talked a lot, it's actually not a lot of things we covered here. Really, what's a radian? Some review of angles in standard position, and what's a coterminal angle. Okay, not a lot here. I'm never going to say any of this is easy. And I think it's probably time for me to stop talking.